So here's the end result of one of our evolutionary simulations where it's discovered that the front appendages do not need to contribute to locomotion. So it in essence becomes a quadruped, and the arms are only used for object manipulation. We then performed a different independent run, but all the aspects of the evolutionary system were exactly the same. In this case, because of historical accident, it discovers this sort of bouncing gait where it uses all 6 legs. So while it's locomoting towards the object, all 6 legs are involved in locomotion. Once it reaches the object, the front appendages are used for object manipulation. So here, we're able to ask new research questions, which is given n body parts, and you can specify those body parts however you like. Here, n equals 3 segments. How are those different body parts going to be distributed in terms of responsibility for the different behaviors? In this case, the forelegs specialize for locomotion, the front appendage just for object manipulation. But that doesn't always happen. Okay? If we were to start this experiment with a wheeled robot and a gripper, we've already made an implicit assumption about the distribution of responsibility. The wheels are going to take care of locomotion, the gripper is going to take place of object manipulation. Okay? By thinking carefully about the robot's body plan, we can relax that assumption and see what sorts of solutions artificial evolution comes up with. Okay, so those are sort of 6 lines of evidence. These are 2 new lines of evidence that have come out of my lab recently. The first one involves object manipulation. We've heard a lot about object manipulation today, so this fits in quite nicely with our previous discussions. Here, again, I'm just going to show you the end product of an evolutionary simulation where we're selecting for 3 competencies in parallel. Okay? So the fitness function, or the objective function that's measuring the quality of any one robot, is looking for 3 things. First of all, grasping. So it's looking for how quickly and how tightly the robot arm grasps these differently shaped objects. Lifting is pretty straightforward. In the simulation, it's measuring the maximum displacement of this object. And the third component is active categorical perception. So we've heard a little bit about that today. So our robot here, does not have a camera. So if you imagine closing your eyes and trying to reach out on your desk and identify objects by shape, that's in essence what our robot is trying to do. Okay? So if you look carefully again at this video, you'll notice that it's grasping first a sphere, then a cylinder, and then a cube, and you'll see it grasps these objects in different ways. Okay? And I'll come back to that in a moment. It turns out that this is a relatively difficult task because some of these things are antagonistic. Okay? If you try and optimize grasping, it's going to grab all the objects in the same way. It's just going to clamp its hand around the object. But if it does that, it doesn't generate the necessary different tactile sensations that will allow it to distinguish between the different objects. Okay? Also, lifting is easy if you just close 2 out of 3 of your fingers rather than grasping tightly. So it becomes increasingly difficult. We can select for 1, 2, or 3 of these behaviors together. If we just evolve for grasping, for instance, okay, and we do one experimental regime in which the body plan is fixed, and a second evolutionary regime in which it can also evolve aspects of the hand, okay, you get the same result. It's able to come up with a good solution for grasping pretty easy. It doesn't matter whether you evolve the morphology or leave it fixed. As you scale up from evolving for just grasping to evolving for grasping and active perception together, where you're trying to evolve these 2 competencies, you start to see a divergence. It continues to be easy to evolve grasping and active perception if the body is evolving as well. But if you leave the morphology fixed, it falls behind. So you start to see a widening gap in performance between regimes in which you evolve the body plan or leave it fixed. So the result from this is that as the tasks we're after become more challenging, okay, as we try and scale up to more and more complex behaviors carried out in parallel or carried out in sequence, it becomes increasingly useful to evolve the body plan along with control. And I'll show you some results that back that up. That's object manipulation. In the last experiment I'm going to show you, what we do is we combine evolution and development, but in a very, very simple way. So this is a very minimal experiment, as you'll see in a moment. It was inspired by the minimal cognition approach of Randall Beer at Indiana University. So we start with a very, very simple quadruped, which you'll see down here. This is, again, the end result of an evolutionary process. We're evolving quadrupedal locomotion towards the target object that you can see off there in the distance. What you'll notice about this evolved solution is that the